Hi, in this lecture we will work out the problems given in exercise 2.2.3. So these were problems involving integrating factors. So let's do them one by one. The first ODE was this particular one with, let's just use the space for rough work. For the first ODE, this quantity, the one that is attached to with dx, was m. This was this whole expression of x squared y minus 2xy squared, and the n, which is the expression with dy, that of course is 3x squared y minus x cubed. Now if you look at this, if you look at both the m and the n, these are both homogeneous functions in x and y, homogeneous to the of degree 3, because if you examine each term in m, for example, this is a term of degree 3 because the power 2 comes from x and there's a 1 that comes from y. Similarly, the 1 comes from x and 2 from y. So this is a degree 3 function, a homogeneous function. Similarly for this one, this has degree 3, this too has degree 3. So m and n are homogeneous, so they are homogeneous of degree 3. And for such problems, for ODEs with these homogeneous m and n, the integrating factor was just 1 over mx plus ny, given this expression was non-zero. Okay, that was one of the rules. So if you just calculate this expression, this comes out to be 1 over, you multiply x with m, so what you get is x cubed y minus 2x squared y squared, and then you add y multiplied with n, so that is 3x squared y squared, and then a minus x cubed y. So these two extreme terms will cancel. These two will add to give you one quantity of x squared y squared. So that is just 1 over x squared y squared. That's the integrating factor. Okay, so if this is the integrating factor, multiplying this factor with, or multiplying it to this ODE will render it an exact ODE. Remember, these are examples of non-exact ordinary differential equations. So multiplying this with IF, which is the integrating factor 1 over x squared y squared, makes it what? Makes this one 1 over y. The first expression becomes 1 over y, and the second expression becomes 2 over x. Okay. Is that correct? Yes. That's with dx. And then this becomes 3, the x squares will cancel, you will have 3 over y, and then minus, you will have x with a y squared dy equals 0. Okay. Now, in fact, if you sort of reshuffle the terms, you see this 2 over x with dx is a good term, because once you integrate that, you should get log x. Okay, similarly for this one, 1 over y with dy, integrating that you get a log y. So those are the easy ones. So the mixed terms are the 1 over y dx and minus x over y squared dy. Those are the mixed terms. So if I sort of write down the mixed terms, so this one is dx 1 over y with dx and minus x over y squared with dy, and this of course we know as d of x by y from one of the exercises that we have done in the notes. And the other one is just log x and log y. So this whole expression here is just going to be x over y. Okay, that's coming from the mixed terms, and the one from the pure terms, this is just going to be minus 2. We're just integrating inside this bracket. So 2, I'll take the natural logarithm, okay, and then a plus 3, the natural logarithm of y, and that's 0. So this is the d of this expression, this function of x and y, which should give you this one. So the general solution for this is just going to be this expression equal to some arbitrary constant. So that's just x over y minus, well, you can just sort of write this as the natural logarithm of y cubed over x squared equals c. Okay, this 3 goes there, this 2 goes there, there's a minus sign, so the x squared will come down. So that's the general solution for the first one. Okay, let's do the second one. For this one, the m and n are these two. So m is 2xy plus e to the x, and n is minus e to the x. So here there is no question of homogeneity. We have to look for other terms, other things. So the one thing that we always do is we check whether this expression, what this expression comes to. Okay. Of course, if they were exact, these two would be the same because that's the condition for exactness. But because it's not exact, this should come out to be something other than 0. So let's just work that out. So if I differentiate m with respect to y partially, I should get a 2x from here, and this should give me just a 0. And then if I just a minute, let's see if I've copied this correctly. Yeah, 2xy, right. So that's just 2 with respect to y is just going to be 2x. And for this one, I'm not sure if, because this doesn't, oh yeah, there's a y over here, so I missed that. There is this y over here. So in fact, let's just put the y squared. So that's the m, right? Okay. So it's not 2x. If you differentiate this with respect to y, you're just going to get 4xy. Okay, the 2 from here comes down, and this y gets a power 1. And from here you get a plus e to the x. Okay, and then if you differentiate n with respect to x, you just get e to the x because it's exponential, but with a minus and this minus, you get a plus, so you get 2 of them. So from here, you get 2xy plus e to the x. Now, if you see, if you see, this is the same as if you had taken this out. If you had written the y outside like it is written, like it is written here, then this is the same expression as this factor in m. So a little bit of manipulation will show you that this is 2 over y, if you just multiply a y and divide by a y, you get a 2 over y here, and multiplying this with y should give me m, and that's the expression. So this factor here, or the del m del y minus del n del x, that gives you a function of y. This was one of the rules. It's a function of y, which we call gy in the notes, multiplied by this m. Okay, and for that the integrating factor was just e to the minus integration of g dy. Okay, and what's that? That's e to the minus, what is g? It's 2 over, so the 2 is a constant that comes out, 1 over y dy. Now that's a log y. Okay, and in fact what you get here is e to the log y to the minus 2, okay, which is 1 over y squared. So the integrating factor is 1 over y squared. So if you multiply this integrating factor to this differential equation, what you get is this 1y will cancel with 1y here, so this is gone. So you're left with 2x. So for this expression there's a y squared that cancels with the y squared, so you're left with just the 2x plus e to the x over y, that's with dx, minus e to the x over y squared dy equals 0. Now this term is the easy one. X with the dx, that's just integration. 2x dx is the total differential of x squared. And this is a mixed term, which is e to the x over y dx minus e to the x over y squared dy. That of course is d of e to the x over y. Okay, because when you do the partial differential of this with respect to x, you get this expression back with dx. That's the formula for a total derivative. But then you do the partial derivative of this with respect to y, you get a minus 1 over y squared. The e to the x remains as it is, and that comes with a dy. So that's the expression. So really what this is the d of this expression from the mixed terms, which is e to the x over y, and then this one is just plus x squared, okay, equals c. So the general solution is e to the x over y plus x squared equals some arbitrary constant c. That's the general solution. Okay, let's do the last one. For this, again, there's no question of homogeneity, but we will look at the same quantity here. So m for this particular problem is 2 sine y squared, and n is xy cosine y squared. Now we'll look at the same quantity first. Del m del y minus del n del x. Well, differentiating this with respect to y, the 2 remains here, that's a constant. This gets me a cosine y squared, and then the differentiation of y squared is a 2y, so the 2 becomes 4 and a y over there. Okay, and minus for this one with respect to x, you see the whole of this is constant, the expression in y, because you're differentiating partially with respect to x, so that's just minus y cosine y squared, and that's just 3y cosine y squared. Now what can this be? So this y cosine y squared is this factor. So in other words, what you can do is you can divide this by x, 3 by x, and you can put in an x there. Once you put in that x, you get the expression n. So that's a function of x with n, and that was again one of the rules. So the integrating factor for this problem would be e to the, well, no minus this time, just the integration of f dx, which is the integration of 3 is a constant, so 3 integration of 1 over x dx, that's log x. So that's e to the log x cube, okay, and that's just x cube. So in other words, you just have to multiply this whole thing by the factor x cube. Let's just do that. So this expression becomes 2x cube sine y squared dx plus x to the 4 y cosine y squared dy equals 0. Now, well, if you look at it, what can be this written as? D of what equals 0? Well, here I think what's missing is a 2. If this, in this expression, there's a dy, so you're differentiating with respect to y. So the y squared got differentiated to a y. I think you need a 2 multiplied everywhere, and then that's just that'll be d of x to the 4 sine y squared. Let's just see if this is this, okay? That's what I can infer from here. The partial differentiation of this with respect to x is, this is constant then when we're differentiating this with respect to x, so you get a 4x cube. So partial differentiation, so I'm using the formula for total derivative. So df is del f del x dx plus del f del y dy. That's what I'm using. So let's just do that for, if this is my f, del f del x is just 4x cube. The sine y squared remains constant, okay, with dx, plus, well, this del f del y with respect to y should be this x to the 4 is constant now. Now differentiating y should give me cosine y squared, but then I have to differentiate the y squared, which gives me a 2y, so 2y. I think that's the expression, okay? That's how I inferred that this is this. So from here, of course, the general solution is x to the 4 sine y squared equals some constant c, and that's the general solution. So really, it's just putting all those rules to use and solving the 3 problems in exercise 2.2.3. All right, thank you.